Okay guys, welcome to 10.8 Electronegativity and Polarity. This is the last section in chapter 10, so we will be coming up on a test here pretty quickly. So if you're not clear on some of the other concepts from this unit, you should go back and watch some of those other videos. Additionally, if you're not clear on some of those previous topics, that's Lewis structures and geometries, we are still building on those two things in today's lesson. So if you're not clear, go back and watch those and make sure you have a good understanding of those first before you start to delve into 10.8. Okay, here we go. So electronegativity, what is it? So electronegativity depicts how electronegative something is, and how electronegative something is will tell you the likelihood that an electron is going to want to group around an individual atom. So the higher something is in electronegativity, the more likely it is that electrons are going to want to be grouped around that particular atom. So what I'm saying is not all electrons are always evenly shared between two atoms that are bonded together. So sometimes the distribution of those electrons are actually closer to one than the other, and it's generally the one that is more electronegative. So what we're going to be talking about is how do you determine which one is more electronegative. For instance, let me just remind you, by the way, these are going to be taking place in covalent bonds. And covalent bonds are going to be nonmetals paired with other nonmetals. So that means electrons are going to be shared rather than transferred. And remember, we see a transferring of electrons in ionic bonds. So let's look at hydrogen and oxygen. So hydrogen and oxygen. Oxygen is more electronegative than hydrogen. So as a result, more of the electrons are found surrounding the oxygen atom. And this means that this is unequally shared, right? So oxygen has more electrons around it than hydrogen. So what does that mean? That really means that each side of this bond of this compound is actually going to have what we call a dipole moment. And a dipole moment is a separation of charge within the bond. And generally, whatever side is more electronegative is going to have a partial negative charge. And we write that partial negative charge by using a delta, looks like an S sort of, by using a delta minus or a delta positive symbol. So in this case, in our oxygen-hydrogen bond that we're looking at here, oxygen is more electronegative. There are more electrons surrounding this oxygen, and it has a partial negative charge. And the side that has less, the hydrogen side, is going to have a partial positive charge. This is creating what we call a dipole moment. This is a separation of charge. And the way we would draw this dipole moment in is we would say that the arrow is pointing toward the more negative side. And I like to think of it like this because the plus side, this little plus, is going to be backed up to whatever the positive, more positive side is. Now, the greater the difference in electronegativity between these two atoms, the greater the dipole moment is. And the greater the dipole moment is, the more polar the bond is. So as we start to talk about polarity here, covalent bonds that have dipole moments are called polar covalent bonds. So this is a covalent bond, two nonmetals, but it is also a polar covalent bond because it has a dipole moment. It's creating an uneven or unequal distribution of electrons, and it's making one side more negative and one side more positive. So we call this a polar covalent bond. So we're adding another word to our vocabulary to describe this particular compound. Okay. Now, how did we know oxygen was more electronegative other than I told you oxygen was more electronegative? Well, you can reference the periodic table. So electronegativity is a trend on the periodic table, and actually this periodic table I gave to you. I just put it in Canvas. It's under your resources tab. It's all the way down at the bottom of your Canvas page. It looks just like the one in this PowerPoint. So the red numbers are the relative electronegativities of each element on the periodic table. And then the red arrows depict the trend. So as I move from left to right across the periodic table, I see an increase in electronegativity. And as I move from top to bottom, I see a decrease. So if I'm looking here, I start at potassium with a relative electronegativity of 0.8, and as I move to the right, I go all the way up to 3.0. Here, when I look at hydrogen, I have a relative electronegativity of 2.1, but as I move down, I go all the way down to 0.7. So these are the relative trends. I highly recommend having this printed out or at least open on your desktop as you start to move through these problems so that you can quickly reference them. Okay, now it is possible that two atoms have the same electronegativity. In this case, there is no dipole moment, which means there is no side that's partially positive or partially negative. We don't see that, right? And if there's no dipole moment, then there's no polarity. This means that there's no polarity. And if there's no polarity, we would say that it's nonpolar. So you can be polar covalent, and that's if you have a dipole moment, covalent, or you can be nonpolar covalent. And that means that you have no dipole moment, nonpolar covalent. So I'll write here, with polar covalent, you have a dipole moment, which we just looked at, and then if you're nonpolar covalent, there is no dipole moment. The two electronegativities are the same. So in this case, if I'm bonding together two Cls, their electronegativities are going to be the exact same, 3.0 and 3.0. So because there is no difference, there's no plus or minus charge, partial positive, partial negative, so there's no dipole, so there is no polarity. So we are nonpolar covalent, but chlorine is a nonmetal paired with a nonmetal, so nonpolar covalent. Now, on the flip side, if there's such a large difference in electronegativity, then we would call this just an ionic bond. And we know normally we see this between metal with a nonmetal, and that is called an ionic bond. And in that case, the electrons are going to be transferred rather than shared. So electrons are transferred rather than shared. Okay. Finish this up for you guys. Perfect. Okay, so here's kind of like a little summary table. So here are the three bond types we just discussed. There's nonpolar covalent, polar covalent, and ionic. Now, notice this is sort of the big thing here, this electronegativity difference. So with this, you're going to calculate what the difference is, and then you'll be able to tell what type of bond you're looking at. So for this first part, let's say I want to know what the electronegativity difference is between oxygen and hydrogen. So if I want to know the difference between oxygen and hydrogen, I can go to my periodic table and I can say, okay, oxygen is 3.5 and hydrogen is 2.1. So oxygen is 3.5 and hydrogen is 2.1. And I always subtract the smaller one, 3.5, from the bigger one. And this is going to give me 1.4. So I have an electronegativity difference of 1.4, which puts me in the intermediate category, which means oxygen bonded to hydrogen is a polar covalent bond, which we already knew, and it is going to have a dipole moment. And because oxygen has the higher electronegativity, this is going to be the partially negative side, and this is going to be the partially positive side. So it will look something like this. Oxygen, hydrogen, with this being partially negative, partially positive, and my dipole moment going this direction, okay? So your job is going to be to our first step is going to be to calculate electronegativity difference and determine what bond type we might be seeing. So that's what you're going to do here. So you're going to identify the type of bond that forms between each pair of atoms as either polar covalent, nonpolar covalent, or ionic. And here are your three options. Your hint here is to reference the electronegativities periodic table and electronegativity summary chart to make your determinations. This is your summary chart, and this is your periodic table. Go ahead and pause here and work on these three, and then we'll go over the answers together. Okay, so let's look at the first one, SR and F. So SR has an electronegativity of 1.0, and fluorine has an electronegativity of 4.0. I take my higher one, 4.0 minus 1.0, I get 3.0. This is a massive difference. This is actually an ionic bond too. So this is a metal paired with a nonmetal, metal paired with a nonmetal. So I can clearly identify this one as an ionic bond. In this one, I've got nitrogen paired with chlorine. So I have two of these. They actually have the exact same electronegativity. So my electronegativity is 0. So that means there is no dipole moment. No dipole moment. And if there's no dipole moment, there's no polarity. And if there's no polarity, I would call that a nonpolar covalent bond. And in this case, I've got nitrogen and oxygen. Nitrogen has an electronegativity of 3.0. Oxygen has one of 3.5. This gives me a 0.5 difference, which is intermediate on that scale. Intermediate difference, which means it does have polarity because it does have a dipole. So this is going to be a polar covalent bond. And again, if I were to draw this out, oxygen is slightly more electronegative. So more, this is not a great drawing, more of the electrons are going to be centered around oxygen. So this side will be slightly negative, this side will be slightly positive, and this is where the direction that the dipole will travel in. Kind of looks like a turkey leg a little bit. So we would call this polar covalent. Okay, so we're close here. So polar bonds and polar molecules. So now let's look at what a polar molecule looks like. So previously we were talking about polar bonds. Now we're going to talk about polar molecules. So let's look at an example. So polar bonds that add together, what is a polar molecule? It's polar bonds that add together, they don't cancel each out to form a net dipole. So that's kind of wordy, but essentially that means you're going to have many polar bonds within your molecule that are going to add up to create a dipole moment. If you have an even number that cancel each other out, then it's not going to form a dipole moment, and you're going to have a non-polar molecule. If you have ones that don't cancel out, you have a bunch of polar bonds that don't cancel each other out, then you're going to have a polar molecule. So let's look at what this looks like. So let's look at CO2, for example. So the first thing you have to do to start this finding of the process out, finding out if your molecule is polar or not, is to actually draw the Lewis structure out. So for CO2, I drew my Lewis structure out, and I have two double bonds, and I have a few lone pairs, 1, 2, 3, 4 lone pairs on here. And then, but it's symmetrical. So we would say that this is going to be linear. I know that if I draw this out, this is going to be linear. So its geometry is going to look something like this. It's going to be all lined up in one row. My middle three-dimensional dot is going to be carbon, and then my two outsides are going to be oxygen. And I'm going to have about 180 degrees in between each of these. They're going to be really, really far apart. Remember, that's what we talked about with geometry. And then I'm going to find out where my polar bonds are. So I have two bonds here. I have an oxygen bonded to a carbon, and I have an oxygen bonded to a carbon. So oxygen has an electronegativity of 3.5, and carbon has an electronegativity of 2.5. So that's a 1.0 difference. So that is actually going to be, that would make oxygen more electronegative than carbon. So there's going to be a dipole moment here. This one will be partially positive. And my dipole moment will be heading towards the oxygen end. And I'm going to have another one on the other side, another partially positive or partially negative charge over here. And I'm going to have two dipole moments. Now, these two dipole moments, remember, we're looking for if this molecule is polar or not. And in order for it to be polar, they have to form a net dipole. In this case, they don't form a net dipole because these are going to cancel each other out. So this bond is actually non-polar. Even though it has two dipole moments, which we just identified, they cancel each other out because one is going this direction, one is going that direction. This is considered non-polar. So we do have polar bonds, we do have dipole moments, but we are still considered nonpolar. Now here, water is kind of a unique one, and that's due to its bent shape. It has lone pairs that cause it to be this shape instead of linear, and we have oxygen bonded to hydrogen. Here's our difference in electronegativity. Water is actually going to be polar because these aren't going to cancel each other out. They're going to be all coming in towards this oxygen. This will not cancel this out. So this is actually going to be polar. Okay, so how are we determining if something is polar or nonpolar? So in order to make this determination, first you have to determine if there are polar bonds. So are polar bonds even present? And that's what we did here. Do we have dipole moments? So does it contain polar bonds? So look for dipole moment. And we look for dipole moments by comparing electronegativities. Look for dipole moments. And determine if the polar bonds add together to form a net dipole moment or if they cancel each other out and form a nonpolar molecule. And you have to draw the Lewis structure and geometry to really make this determination. Okay, so you're going to give this a try. Determine whether the molecule is polar or nonpolar, and there are two examples here. So pause and do this you try, and then we're actually almost done here. This is the last slide, is going through these. Okay, so let's take a look. So your first example was NH3. So the first thing I did, step 1, draw the Lewis structure, which I did. Now, it has 3 things around it. Actually, I'm sorry. This has 4 things around it, 1, 2, 3, 4. So its electron shape is tetrahedral, but because one of them is a lone pair, it's actually trigonal pyramidal. So we're going to get something like this, and I probably should have drawn this a little bigger, actually, and I'm going to do that right here, right now. So you're going to have some sort of shape like this, okay? And with this being your nitrogen and these being your hydrogens coming off, okay? Now in this case, we have nitrogen with a 3.0 electronegativity and hydrogen with a 2.1. So this has 0.9 as its polarity, as its electronegativity and difference in electronegativity. So this means that there are going to be dipole moments. So the dipole moment is going to favor the nitrogen, so they're going to move towards the nitrogen. This side's going to be partially positive, and this side's going to be partially negative. And we actually have 3 of these. 1, 2, and 3. And because these don't cancel each other out, we have an odd number. This is going to create an overall net dipole moment. We're adding together 3 dipoles. So as a result, this is going to be a polar molecule. Okay? Now here, our next one is CH4. So first thing I'm going to do is draw out the Lewis structure. 1 carbon as our central atom and 4 hydrogens around it. This has an electron electron geometry of tetrahedral and a molecular geometry of tetrahedral. I'm going to draw my 3-dimensional shape. It's going to look something like this. And this is going to be with carbon being my central atom and my hydrogens being all surrounding this. Now, this does have a dipole moment. So the carbon is going to be slightly more electronegative than the hydrogen. But because there are 4, 1, 2, 3, 4, these are actually going to cancel each other out. Cancel out. So this one will cancel this one, and this one will cancel this one, and we're actually left with a non-polar molecule. So there are 4 dipole moments that happen in this bond, but it's non-polar because they don't create a net dipole moment. No net dipole moment. By the way, this is called a hydrocarbon, and hydrocarbons typically are all nonpolar. So if you see some variation of carbon and hydrogen bonded together, some hydrocarbon, it's probably going to be nonpolar. Okay, if you have questions, we'll talk about this more in class, but hopefully this helps, and go ahead and do the practice problems that are associated with this, and make sure you submit your U-Tries on Canvas. Thanks, guys. Have a great day.